there, and then that'll be spring break after that. So awesome. Cool. All right, so let's go through this last section then. So 14.6 is descriptive statistics, which is actually the same as last section, except this is graphical, whereas that was numerical. Okay, so we're going to be looking at a lot of graphs today. So we have numerical data, which is data whose values are real numbers, and then categorical data are data that tell us whether an individual does or does not belong to a particular category. So I said last section, the difference between these two is that numerical data would be like if I asked everyone in the class what was their height in inches. All right, we could find the mean, median, and mode on that, right? Categorical data would be like if I asked everyone in the class, what is your favorite color? Okay. And then we really cannot find the mean nor median of that because, like, what's the mean of red and blue? Like, I don't know, that you can't do that. We could still do the mode though, right? The mode is the 1M that we can still do on the categorical data, okay? We talked a little bit last section about frequency tables, and we're going to continue with that. So frequency is the number of observations in an interval. And then frequency table groups a set of data values into intervals and shows the frequency of each interval. All right. Next up, we're going to talk about histograms. So a histogram is a graph that can display data from a frequency table. And a histogram gives visual representation of how data are distributed in different bins. Okay, so I'll go ahead and show you what a histogram looks like. A histogram looks like this, okay? You've probably seen them before. You'll often hear people call these bar graphs, okay? I think that those terms are pretty much interchangeable. I've heard some people say that if the rectangles have no space in between them like that, that's technically a histogram. And if they have space in between them, that's technically a bar graph. But honestly, I heard people call this a bar graph before, and I wouldn't even correct them. I think that it's fine to use these interchangeably. So I'll say here, AKA a bar graph, okay? Couple advantages to calling them a histogram. The first, of course, is that you could post a histogram to your Instagram, okay? So that would be very good. So if today after class you want to post a histogram to your Instagram, I'll give you some extra credit, 0 points extra credit for that. So that's nice. The other thing that's nice for you guys about a histogram is that since you guys aren't 21 yet, you're not allowed to go into a bar graph, okay? That was another joke there. Get it? Bar graph. Actually, all the bars are closed now because COVID. So I guess I'm not allowed to go to a bar either. Okay, so it's all histograms all the time. We can still go on histogram. Okay, all right. Next thing we're going to talk about is the shape of these histograms. All right, and we have three main shapes here. There are some that don't fit into any of these three categories, but these are just kind of our three main ones. So the first one's called symmetric. Okay, so symmetric means it's kind of the same on both sides, which I think you can see there, correct? And the big idea on the symmetric is that the mean is, and I'm going to do a squiggly equal sign there, is equal to the median. Sometimes it's not exactly equal. That's why I put this squiggly equal. Sometimes it is, but sometimes it's just like close, okay? Next up is skewed right, all right? And then skewed left, okay? And we'll compare and contrast these. Now, some people may be thinking I mixed these up, like, hey, Mr. Berry, this one should be skewed left because most of the data is on the left, but that's not true, okay? I put it correctly. So for skewed right, I always remember the little trick is I would want to ski to the right. I like to do a little snow skiing myself. And so if I was at the top of this hill right here, which way would I want to ski? Well, if I skied to the left, it's literally a cliff, right? But if I skied to the right, it looks like a nice little run here. I would have some fun going down this little steep part, and then it kind of mellows out, and then go back to the chair, and then go back up to the top of the mountain, okay? And so that's the way I think of it. Now, if you want to know why it's really called skewed right, It's because the mean is greater than the median. The mean gets pulled to the right. Okay, so the skew describes the mean. And they showed it on the picture there. You can see the mean is to the right of the median. All right, so why does the mean get pulled to the right? Well, we talked about last section that outliers affect the mean, but don't really affect the median, correct? So we have these like a few data points on the far right of this graph. They pull the mean towards them without really affecting the median, okay? So conversely, with the skewed to the left, which I would want to skew to the left on this one, the mean gets pulled to the left because we got a few data points, a few outliers on the far left that are pulling the mean that direction. All right, cool. So now let's practice drawing a histogram, okay? Now, when we get these on WebAssign, they're gonna tell you the bin size. So I'm gonna go ahead and write down the bin size here in black. So let's just pretend that that was part of the instructions, okay? So let's say bin size, and I'll explain what that means here. Let's say it's 5. And let's say we're gonna start at 1. So like I said, on WebAssign, they're gonna give you that information. So let's pretend that that was part of the instructions. That's why I wrote it in black, okay? So we're gonna start at 1. This is gonna be my first bin here. My first bin is gonna start at 1. And my first bin needs 5 numbers in there, okay? So it's gonna go from 1 to what number? Well, some people would say 6 here. Some people would say 5. I would say if you ever have a doubt, no shame in this, counting on your fingers, okay? So let's count 5 numbers on our fingers. 1, 2, 3, 4, 5. So that would mean I go to number 5. The next bin then is gonna start at 6. I'm gonna count on my fingers again. I'm not gonna be a hero here. 6, 7, 8, 9, 10. So if I went to 10, that would represent 5 numbers. It looks like there's 4 in each bin, right? Because like 5 minus 1 or 10 minus 6 is 4. But remember, if you're including those numbers, there's always one more than you think. The other thing I kind of think about is if you look like vertically, and the next one's going to be 11 here, like 1, 6, 11, that's where the 5 gets added, okay? So I can do that trick on the other side too. So this is going to be from 11 to 15, and then 16 to 20. Awesome. Okay, so now we're going to tally these up. So I just kind of, you don't really have to go in order here. I just go like, here, that's a 7. I put a tally right there. I cross it off and then put a tally in the correct bin. All right, so 17 down at the bottom, 14, 2, 7, 9, 5, 12, 3, 10, 4, 12, 7, 15. All right, so I got 4, 5, 4, 1 for my frequencies, right? Awesome. All right, so when you draw your histogram then, the y-axis is your frequencies. So my max frequency was 5, so I'm gonna go up to 5. My first bin has a frequency of 4, and it's from 1 to 5. Then I have a frequency of 5 from 6 to 10. Then I have a frequency of 4 from 11 to 15. Then I have a frequency of 1 from 16 to 20. Beautiful histogram, all right. All right, let's try that one more time. This one, let's pretend there were instructions that said bin size 6. start at 0. I needed to start at 0 on this one anyway, because you can see we have a data point at 0. If they didn't give you a bin size, which I'm telling you they are going to, but if they didn't, you just have to make sure you're doing a bin size that would allow you to kind of fit all of the data in there, okay? So you could try something out, and if you're kind of have some numbers that are too big, you have to redo it, okay? All right, so this one, we're gonna start at 0, and if my bin size is 6, I'm gonna count on my fingers, so 0 does count. 0, 1, 2, 3, 4, 5. If I go all the way to 5, that does include 6 numbers. Now, the next one is 6, 7, 8, 9, 10, 11 would be 6 numbers. Now I can kind of go vertically here and just add 6 vertically, and then add 6 vertically, and there we go. Okay, so then I got a 7, 10, 1, 5, 14, 22, 6, 8, 0, 11, 13, 3, 4, 14, 5. So you can see for the frequency for this one, I'm just leaving it as tally marks instead of numbers. Is that okay? Sure, why not? All right, we can count the tally marks. All right, so my max frequency is 6, so I'm gonna have to go up to 6 on the y-axis here. And that is actually my first one. On the previous one, I put on the bottom 1 to 5. Sometimes you'll just see them put the biggest number right here. So that means that that one is included in the lower one. So this is like from 0 to that 5. So if it is exactly 5, it goes to the left. So then the next one would go to 11. The next one would go to frequency of 3 would be to 17. And then the last one would go to 23. So I did it 2 different ways there. You can see on the bottom on the x-axis, because I see it written those 2 different ways. So I think that both of those are acceptable. So I just wanted to expose you to both kind of ways of doing that. All right. All right, let's move on, because what I think is infinitely more important than drawing a histogram is interpreting a histogram. So let's do that now. Okay, so the accompanying histogram shows the heights of the students in Kyra's health class. How many students are in the class? So for this, I would just add up the frequencies. So 2, 4, 5, 4, 1, right? For those frequencies. If I add those up, it comes out to 16. So that's how many students are in the class. Describe the distribution. I would say symmetric on this one. Now you can see Ms. Azamora's answer key here says somewhat symmetric. I would agree with that as well, because it's not perfectly symmetric, correct? The middle 3 are actually perfectly symmetric, but then when we get to the outside, it's kind of off by 1. For me, that's close enough that I'm just going to call it symmetric and be okay with it. If you said somewhat symmetric, I agree with that as well, okay? All right, state a height that could be the median, all right? So what's a height that could be the median? Well, remember back to what we set up here, that in the symmetric distribution, the mean is equal to the median, but it's also right in the middle, okay? So the median must be in this middle bar. So you can see the answer key there says it could be 184. Now, could it be 185? Yeah. Could it be 186? Yeah. Could it be 189? Technically, yes. Okay, honestly, this could be any number between 180 and 189. Because that middle bar there, do I know where, what numbers are in there? Not really, right? Could it be 5 numbers that are all 180, 180, 180, 180, 180? Yes, it could, technically, yes. Could they be all 189s? Yes, they could be all 189s, okay? So I don't know how that data is spread out there, so this is really an estimate, but I know it's got to be somewhere between 180 and 189. Most likely, those 5 numbers are kind of spread out pretty evenly. And so it probably is somewhere closer to the middle, 184, 186, somewhere around there, but I really don't know that, okay? All right, let's move on. Another one here. The first thing I notice here is the distribution, okay? And I know that's part B, but I'm gonna answer it right now because this is such a classic skewed right. You can see we have a lot of data on the left and then outliers on the right. So that's our skewed right. That's where the outliers are. Okay. How many people called the customer service center? So that's like, yeah, what's our N? So this is definitely going to be an estimate. I think you can see this is really tough to see what these numbers are. As I'm reading these, I would probably call this one like a 67. Más o menos, right? Like if you said that was 68 or 65, like I'm not going to argue with you. This one I would say is about 17. This one looks like a 6, a 5, and a 4 to me. And I would say that's a 1 and a 1. Once again, if you disagree on any of those, I don't want to argue. Yeah, you can't really tell anyway. So I would give up on the argument. All right, so I got 101. You can see Miss Asmore did this. She got 110. I think that's fine. I honestly think that any number you got that's between 90 and 110, I would say is acceptable because it's just not possible to tell exactly. Okay, so that is why it said estimate. I think you should have gotten a number between 90 and 110 though. All right, in what range is the median? Okay, in what range is the median? Now, here's how I'm going to do this one. Okay, so let's say that there are 101 people. That would mean that the 50th person is the median, right? If I line them all up in a row, 101 people, the 50th person is the median, or maybe be the odd number, or maybe be the 51st person. Either way, it actually doesn't matter. We're going to see in a minute here. So where is the 51st person? Well, we have 67 people in the first category, right? So I'm going to say that the median has to be in there, right? Because the first 67 people are in there. So of course the 51st person is there. The 50th person is in there. The 52nd person is in there. Even if I had Miss Azamore's estimate of 110, that would be like the median is the 55th person. They would still be in there, correct? So the median has to be in that range. What is that range? That range is actually 0 to 12.5. It's not 0 to 25 because 0 to 25 you can see is 2 bars, right? So then half of 25 would be 12.5 for that first bar. Okay, let's do some more like this. So graduates of these universities have their salaries written down there. So they're asking, is it symmetric, skewed, or neither? And then determine the approximate location of the median and the mean. Okay, so for A here, it definitely looks symmetric. Once again, not perfectly symmetric, but it's close enough to symmetric that I feel comfortable calling it symmetric. All right, and we'll recall, like I said, for Kyra's, the heights in Kyra's class, when we have symmetric, not only does the median about equal the mean, it's also at about the middle of the graph here. So it's at about 100K. If you said 105K, 110K, I could be down with that. All right, University 2, we get a skewed right again. For the median on this one, I would probably do what we did on this one and count up the data points. So I got 16. This is probably 18. This is probably 13, 10, 6, 3, 2, 1, 1, 1. So I got 71 people, right? If you add all those up, which would mean 35 to 36 would be the median. So where would the 35th and the 36th people be? Well, 16 plus 18 would be 34, correct? So 34 people in these first two bars, which would mean the 35th and 36th people would both be in that third bar. So what is that third bar? It's 70 to 80K. 70 to 80,000 for the median. Okay. Where's the mean? Well, we know that when it's skewed right, the mean is greater than the median. So I would probably estimate the mean, and this one's like really kind of a shot in the dark. I'm gonna say from 80 to 100K. How about that? That one's kind of much more an estimate. But we know that it's gonna be more than the median. That's the key. All right, University 3 now, symmetric. All right, and the median is about equal to the mean, which is about 100K. So those are the easy ones, right? All right, and then this one, we have our first skewed left of the day. I'm gonna go ahead and count up my frequencies here, get my total number of people, or total number of data points. So I got 32 people, which would mean about the 16th was the median. So where's the 16th person? Well, I got 3 up here up front, 1, 2, 3, and then 5, 7, 9, 12, 15, and then the 16th would be right here. So that'd be between 150 and 160K. All right, where's the mean? It's definitely less than that. I would say, let's say between 130 and 150K. It's kind of just usually I go the 2 bars left of that, okay? Perfect, all right. All right, let's continue R. Let's talk about standard deviation again. All right, we're actually not going to calculate it here for graphical. What I'm going to ask you is the standard deviation is, or I'm going to remind you, a standard deviation is a measure of how spread out the data are. If the data is more spread out, the standard deviation is greater. If the data is less spread out, more compact, the standard deviation is smaller. So which one of these has the greater standard deviation and why? So I'm going to say this. I'm going to say section 2 has the greater standard deviation. So section 1 is less, section 1 is greater. This one has a smaller standard deviation because most of the data is in the middle. A little data on the outside and a little data on that outside, right? A little. This one's a greater standard deviation because we kind of have equal data, equal amounts of data on the outsides, in the middle, and on the outsides, okay? Now, if we wanted an even bigger standard deviation, it would be like a lot of data on the outsides and like a little data in the middle. This would be even bigger, okay? So if it's the data's in the middle, that's a small standard deviation. If it's kind of equally spread out, that's a little bit bigger. If it's all on the outside, that's even the biggest. Great. All right, next up. Normal distribution. This is really important and people talk about this a lot in real life, IRL as they say. Most real world data are distributed in a special way called the normal distribution. It's also called a bell-shaped curve. So you might have heard that term. They say this is the bell-shaped curve. They say that looks like a bell. I don't really see it, but okay. I guess I can kind of see it. So very important here, we know that these percentages. So normally distributed data with mean, we're going to call this the mean. I know we had a different symbol for mean last section with the X bar, but this is another symbol for mean. And the standard deviation is that little guy. We did use that one. 68% of the data are between one standard deviation on each side. So that's split up here, 34 in this section, 34 in this section. So if you add the standard deviation to the right, you get 34% of the data and then 34% on the other side. And then 95% of the data is within 2 standard deviations. So that gives you 13.5 on each side here. And if you add up all 4 of these sections, that's what gives you the 95%. And then you have these little sections out here, 2.35%. And then I'll tell you this little piece out here is 0.15%. So I would recommend that you add that in there. Okay. I always think of this graph in terms of like people's height. So like, to me, like most people's height is between 5 feet and 6 feet. So I would put I would say like this is, I would call this 5 feet actually, and this is 6 feet. So I do feel like 95% of people are between 5 feet and 6 feet, right? And then are there people outside of that? Sure, absolutely, okay, but just less of them, right? So I know some people that are like 6'4" and they go in here. And then I don't know anybody, but I know there are people that are 7 feet tall and they're like out here. You know what I'm saying? Okay, so let's say the height of a certain pine tree is normally distributed with a mean of 33 and a standard deviation of 3. Sketch a normal curve that describes the distribution. So we need the mean in the middle, and we should be adding 3 as we go along. So A is already wrong because we got the 30 in the middle, right? B, we got our 33 in the middle, so that's looking good. And then are we adding 3 as we go outside? Yes. Are we subtracting 3 as we go the other way? Yes. Then B is going to be my correct answer. C is incorrect because although we have the 33 in the middle, we're adding 2 as we go outside. All right, the better question I like to ask is questions like this. So this one says a data set is normally distributed with a mean of 31 and a standard deviation of 9. use the empirical rule to find the percentage of data that lie in a given interval. So I would always, with that given information, I would draw my little bell-shaped curve, okay? You put the mean in the middle, and then you go 3 standard deviations out. So this one's gonna be, actually I'm gonna draw this line here. So I add, since the standard deviation is 9, that's what I'm gonna be adding. So I'm gonna make this one 40, and then 49, and then 58. As I go the other way, I'm gonna subtract 9. This is 22, this is 13, and then this is 4. For the percentages, you'll usually only need the middle 4. So these are 34, and then these are 13.5. Where did I get those from? Well, those are actually, those percentages are always going to be the same. That's from this picture right here, okay? So do you have to have all these percentages memorized? Well, we're allowed to use our notes on the test, right? So no, but you have to know where I got them from, okay? So the percentages in each piece will always be the same, 34 on the middle two, and then 13.5 on the next ones, and then 2.35 outside of that if you need it, and then 0.15 outside of that if you need it. What's going to be changing from problem to problem is what numbers go on the bottom, okay? So that's where I got it, the mean in the middle, and just add the standard deviation going right, subtract the standard deviation going left, okay? So what percentage goes between 22 and 40? Well, that would be this piece right here, right? So I have 2 pieces actually there. I have the 34 plus another 34. So that's going to be 68. So I had 2 sections in that one. Both of them were 34, so you add them together. What percentage is between 13 and 22? Well, that's actually 1 section. So I don't need to do any adding. It's 13.5%. And then greater than 31, that's actually out that way. I could write down these 2 pieces, the small pieces, and add everything up. But what's easier is if you're going from the middle forever to the right or the left, that's just going to be 50%. That is exactly half of the data. All right, and we do have time to finish this up on the next page. So let's do that. All right, so IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. All right, so let's draw our bell-shaped curve. So we have 100 is in the middle, and we're going to add the standard deviation. So I got 115, I got 130, and I have 145. And I'm going to subtract going this way. I got 85, I got 70, I got 55. And then my percentages, remember, are standard. So this one's always going to be 34, 34 in the middle. We got, shoot, I always forget this one. What was it? 18.5? 13.5. 13.5. I told you usually don't need the outside pieces. If I need them, I'll look back at them. But for now, let's just do 85 to 115. So that's the middle 2 pieces again. So that's 68 again, like we saw in the previous one. Now they said also here, find the probability that a randomly selected individual has an IQ score within that given interval. So that's just going to be the decimal form of that percentage, because probability we usually do as a decimal. All right, next one, at least 130. So that one is going to be from here out. So I am going to need these little pieces on the outside. So I'll look back at my chart. This one was 2.35%. And this one I said was 0.15%. So I would have to add those up. So the percentage would be 2.5, the decimal would be 0.025. All right, y por fin, at most 130. So at most 130 would mean less than or equal to 130. So that's actually going the other direction from 130. Now you could get all of those little pieces and add them all up. But what's actually easier, since we have this one, we could do 1 minus, actually I'll do 100. So I'll do 100% minus my previous answer, because you can see that previous answer were like the two sides, like the complement, right? They need to add up to 100% or they need to add up to 1. And so that's going to be 97.5%. Okay. All right. Awesome. That was fun. Love me